Bessel functions of various kinds arise in problems in science and engineering. Often they come up when we are dealing with problems that have cylindrical symmetry, or they are described in a spherical region, such as problems of waves, problems of vibrations, problems of oscillations in cylindrical ducts, in tubes, in geometries that are circular. And so what we're going to do is we're going to look at a summary of Bessel functions of various kinds that arise to become familiar with the notation and of the different kinds that arise in different applications, and then we will look at some more details. So let's begin by a quick summary of the Bessel functions. So we're going to encounter Bessel functions that are called just the regular Bessel functions of order nu. And they are going to be denoted by these symbols j nu of x and y nu of x, and these are called the Bessel function of first kind is j nu, and Bessel function of second kind, which is also called the Neumann function, is represented by the symbol capital Y of nu as a function of x. Now both j nu and y nu are oscillatory functions. They are cousins of cosine and sine functions. They both oscillate in space as a function of the independent variable and continue to oscillate and decay as x increases. And for small values of the argument x, they are well behaved. The j nu is well behaved, y nu is not well behaved, it is singular, it blows up as x becomes small. Using these two functions j nu and y nu, which are like sines and cosines, one can define complex valued functions which are called Hankel functions, and sometimes it's called Bessel function of third kind. And depending on the combinations, one can define them to be what is called Hankel function of first kind, h nu with superscript 1 and h nu, capital H nu with a superscript capital 2, and they are like exponential functions with imaginary arguments, so like e to the plus ix and e to the minus ix. And so if we, for example, expand e to the ix, we can write it as cosine x plus I sine x, and so that would be this first analog of this first function. So we can take a j nu of x and add to it this imaginary part of y nu of x, and that together defines the Hankel function of the first kind. And Hankel function of the second kind is simply defined by flipping the sign of the imaginary part, just as for exponential of minus ix, you would flip the sign in describing it as we have written over here. If we put the minus sign, then that would be the representation for e to the minus ix. So that's the regular Bessel functions, and now we will turn to describe the modified Bessel functions. So there are Bessel functions which are non-oscillatory, and they are called the modified Bessel functions. Modified Bessel function of order nu are represented by these symbols, a capital I of nu and capital K of nu. And so just like we have growing and decaying exponential functions, I nu is a growing exponential function and K nu is a decaying exponential function as a function of argument x when x is a positive argument. Both of these functions are non-oscillatory, they do not oscillate, they behave like exponentials. For small values of the argument, I of nu of x is a well-behaved function, but k nu of x is a singular function, it blows up for small values of x. Further note, in terms of an overall summary, that Bessel functions become very useful because they have very important orthogonality properties, and they have recurrence relations which allow Bessel function of one order to be expressed in terms of Bessel functions of other orders, and likewise derivatives of Bessel functions can be expressed in terms of Bessel functions of lower and higher order. So those allow manipulation of relationships that involve these Bessel functions. And so we will now turn to looking at some more details of the Bessel functions, both the regular kind as well as the modified one.